Welcome to The Explainer. Today, we are going to build the blueprint for a service you probably use every single day, maybe without even thinking about it, a URL shortener. All right, so here's the plan. We're going to start with, the why. Then we'll build this thing up piece by piece. We'll cover everything from how to make that tiny link in the first place, all the way to making sure it can handle, the entire internet.
First things first, why do these services even exist?
What's the big problem we're trying to solve here?
You've seen these, right? URLs that are just a complete mess. Super long, full of weird tracking codes, just plain ugly. You're never going to remember that. You definitely don't want to type it out. And forget about trying to share it on Twitter or in an email. It just breaks everything.
So, how do we fix this digital monster? Well, the answer is a URL shortener. And really, it all boils down to two core jobs. Think of it like a digital code check, seriously. The first job is shortening. You hand over that big clunky URL and you get a nice, small, simple ticket back. The second job, redirection. You show them your ticket and boom, you get your original long URL back. And you're sent right there. Simple as that. Okay, so we've got our digital code check idea, but how does it actually work? Let's get into the nitty-gritty of creating that short, unique ticket for every single long URL we get. Well, the secret sauce here is something called base 62 encoding. All it means is we have a system that uses every letter, A to Z, both uppercase and lowercase, plus all the numbers from 0 to 9. That gives us a pool of 62 different characters to build our short links with. It's a really efficient way to make short, unique IDs. And the process itself is actually pretty cool. All we do is start with a unique number, right? Just a counter that goes up. 1, 2, 3, a million. We take that number, run it through our base 62 conversion, and bam, out pops a short, clean little alias like G8. And that's it. That's our tiny URL. Okay, let's follow the data. This whole process is what we call a write operation. We're writing new data to our system. So you send a request with your long URL. Our service then grabs a brand new, unique ID, does that base 62 magic we just talked about, and this is the most important part, it saves the mapping. It says, hey database, remember that this new short link goes with that original long one. Then it just sends the new short link back to you. So making one link, that's the easy part. But what about making a system that can handle billions of links and even more clicks? Now that's the real challenge. We need to think about internet scale. All right, let's talk scale. You have to plan for this stuff. Let's imagine we need this thing to last for 10 years. A decent estimate, we're probably looking at needing to store something like 365 times billion records. That's a lot of links. And all those records need a home, right? That's going to take up about 365 terabytes of storage, and a number that big changes everything. It forces us to be really, really smart about how we design the system, especially when you think about how people use these links. Okay, this right here, this is the absolute key to the whole design. A link gets created once, that's one write, but that same link might get clicked thousands, maybe even millions of times. Those are reads. So you have this massive lopsided ratio. Think like 1,000 reads for every one write. This imbalance is everything. Our entire system design has to be built to handle this specific problem. So how do we do it? We use a really smart pattern called CQRS. It sounds complicated, but the idea is actually super simple. We basically split our system in two. We create one path that's only for writing new links and a totally separate path that's only for handling clicks, the reads. This way, we can optimize and scale each path independently, which is a total game changer. So, keeping that split path idea in mind, let's zoom in on the read path. This is the one that handles the clicks. When someone clicks a short link, it has to be fast, like instantly fast. Every millisecond matters. So here's how we make that happen. Okay, so you click a link, speed is everything. The first place our system checks is not the main database. Nope, that's way too slow. It checks a super fast in-memory cache. If the link is in the cache, we call that a cache hit. We can redirect you instantly. If it's not there, a cache miss, okay, fine, we'll go to the database. But here's the clever part. We grab the link, and then we immediately put it into the cache. So the next time someone clicks it, it'll be a super fast hit. This whole strategy actually has a name. It's called cache-aside. The application itself is basically the smart gatekeeper. It's programmed to always check the fast lane, the cache, first. Only if it comes up empty does it bother to take the slow road to the database. And when it does, it makes sure to put that info in the cache for the next time. It's a classic for a reason. It's simple and it works incredibly well for building fast systems.
Right, but the cache isn't infinite. It's going to fill up. So what do we kick out to make room? That's where a policy called LRU, or least recently used, comes in. It's smart. It just looks at the links in the cache and gets rid of the ones that haven't been clicked on in the longest time. This keeps the cache filled with the hottest, most popular links.
Okay, we've got all the pieces on the table. Let's put them all together now and take a look at the final blueprint for our system. So it all kicks off with you, the user, making a request. The first thing that request hits is an API gateway. Think of it as the ultimate traffic cop. It looks at the request and asks, are you trying to create a new link or are you trying to click on one? And based on that answer, it directs the traffic down one of our two specialized roads. If you're trying to create a new link, you go down the right path. That request goes to a special shortening service. Now, this service needs a unique ID, but asking the database for one every single time would create a huge bottleneck. So instead, it grabs a pre-generated key from a completely separate key generation service. That's a huge optimization. Once it has the key, it just saves the new short link and the old long one into our main database.
But what about all those thousands of clicks for those read requests? Traffic goes down our other, completely separate, super optimized path. It hits a redirection service. And what's the first thing it does? You guessed it, it checks that lightning-fast cache. And if, and only if, it's a miss, it'll go to the database. But it doesn't even bother the main database. It reads from a copy, a replica, just to make absolutely sure it never ever slows down the process of creating new links.
And there you have it. That is the complete blueprint for a URL shortener that's built to handle true internet scale. You know, the biggest takeaway here isn't just about the cool base62 trick. It's about designing for how the system is actually used. The real genius is in recognizing that huge imbalance between reads and writes, and then building two separate, specialized paths to handle it. That separation, plus a really smart caching strategy, is what makes the whole thing fly for billions of users.